Since at the beginning of every session you open, you're prompted to enter a sample rate and bit depth, some years ago a student asked me, what actually is sample rate and bit depth? And I thought I should probably explain it, so this video will attempt to do that and give you a better understanding of what it means. Think of it this way. Digital audio is a computerized representation of analog sound, just as a digital photo is a computerized representation of whatever the camera is focused on. As a digital picture will be less pixelated and a better representation of the real thing at a higher resolution, so will digital audio. In analog to digital conversion, the analog sound wave is cut into horizontal chunks. The smaller the chunks, the closer it approximates the real thing. The horizontal chunk size is called the sample rate, and is typically either 44,100 or 48,000 times per second, although it could be higher or lower. The analog sound wave is also cut into vertical chunks. Just how many chunks is determined by the bit depth. For a bit depth of 8, the sound is divided into 256 vertical divisions. For a bit depth of 16, the sound is divided vertically into 65,536 chunks. However, for a bit depth of 24, there are 16,777,216 vertical divisions, which very closely approximates the actual analog waveform, and is why 24-bit files sound so good. So I've done this in-class experiment in the past. I'll show it to you online. I took a sine wave that initially was 4401 and 24-bit, and I converted the files and made a 4401 16-bit and a 4401 8-bit file from that. Then I brought them into an audition session, and I made the session parameters 4401 and 24-bit, which was the highest sample rate and bit depth for the files I was bringing in. I put them on separate tracks, and when I solo the tracks, they sound identical. You don't really hear much difference. I actually duplicated the track that was the 8-bit track, and I put it out of phase. So now when I play the 8-bit track with the 8-bit out of phase track, everything totally cancels and we hear silence. That's because they're 180 degrees out of phase, and when you add them together at equal volumes, they totally disappear like matter and antimatter coming together. However, something interesting happens when I solo the 8-bit out of phase file with the 24-bit file. If you think about the 24-bit file, it's much better defined than the 8-bit file. It looks more like the actual sine wave because of the higher resolution. The 8-bit file is a bit more jagged. So when we combine those two, what's left is just kind of the jagged edges, and this is what we hear. I call this audio pixelation, and for me it makes a good case for the fact that there are stair steps in the digital WAV file and not simply points. This next video talks about the ideal dynamic range. Ideally, a recording would have enough dynamic range so that the listener would hear all the program material without hearing any distortion in the loudest passages or noise in the quietest passages. The dynamic range of a digital audio signal can be easily calculated by simply multiplying the bit depth by 6. Therefore, a 16-bit recording like a CD using the full 16 bits would have a 96 dB dynamic range. A 24-bit recording, again using all the bits, would have 144 dB, and a 32-bit recording would have a 192 dB dynamic range. To fully appreciate the 144 dB dynamic range of a 24-bit recording, the listener would have to be in an anechoic chamber, the only place where the volume can be 0 dB, the threshold of human hearing. They would also need to be listening to a speaker system that could produce ear-damaging pain levels of 144 dB. However, most listening environments have a much higher noise floor that can be between 25 to 50 dB or more. This noise floor can be lowered about 20 dB if the listener wears headphones, but adding 144 dB more to these levels would probably kill the listener. So, even though there are many other benefits of higher bit depths, the 96 dB of dynamic range that CDs offer is more than enough for any project. This includes classical recordings that generally have 60 dB of dynamic range, 5 times more than other musical genres. A term that you probably don't need to obsess about or spend a lot of time thinking about, but I want you to know what it is dither. And this is a short video about that. When an analog signal is converted to a digital signal, there are quantization errors, which are the differences between the sampled values and the actual analog values. To mask these errors, white noise is added at low levels. This white noise is known as dither and occurs at the low end of the dynamic range. For a 16-bit signal, the dither is 96 dB down from 0 dB full scale. For a 24-bit signal, the dither is 144 dB down, and for a 32-bit signal, the dither is 192 dB down from 0 dB full scale. To increase the apparent signal-to-noise ratio, noise shaping is often used. Noise shaping alters the spectral shape of the white noise. It spreads the dither to frequencies that the ear can't hear as easily at low levels. The result is that the apparent dynamic range for a 16-bit signal increases to about 100 dB. For non-PCM devices like SACDs that use direct stream digital encoding, the dither is shifted into frequencies above the range of human hearing to between 20 kHz and 1.4112 MHz. Doing this extends the nominal 6 dB dynamic range for these 1-bit devices up to 105 dB. So to give you a better understanding of bit depth, this was actually a slide from the textbook that we used to use. And they talk about 1-bit, 2-bit, 3-bit, 4-bit files on this page. A 1-bit file is simply on or off, up or down, 1 or 0. Every time you increase the bit depth by 1, you're adding exponentially 2 to whatever that bit depth is, quantization levels. For example, a 2-bit file would have 4 quantization levels, a 3-bit file would have 8 quantization levels, and a 4-bit file would have 16 quantization levels. So you can see as the bit depth increases, you're defining the file a lot better. Many of the first PCs and even the first affordable digital samplers were only 8-bit. We thought they sounded pretty good, but 8-bit, you only have 256 quantization levels. And the dynamic range of a digital signal, which is the difference between the highest and lowest volume levels in that signal, can be determined by multiplying the bit depth by 6. And obviously, with a higher dynamic range, you get better signal to noise because your noise floor is much, much lower. So for an 8-bit signal, you only have about 48 dB of dynamic range, which is about the signal to noise of a cassette without noise reduction. The file definition increases dramatically when you go to 16 bits. We jump by 2 orders of magnitude up to 65,536 quantization levels. And the dynamic range is now 16 times 6, which is 96, and that's the dynamic range of a CD. And a lot of people feel that's about as good as most humans can appreciate. When we move to 24-bit, the largest number now is a number with 24 ones. We've now jumped 3 orders of magnitude to 16,777,216 quantization levels. And you can see as we increase the resolution here, we're defining that sound wave much more precisely, just as with graphics, when you go from 200 DPI to 1200 DPI, you're defining the image much, much better with much smaller pixels. And now we have a dynamic range of 144 dB. And many people feel that it's really not possible to appreciate that much dynamic range since there's no place that quiet that you can actually hear that much dynamic range. So today, most workstations and software will allow you to do 32-bit floating point. And here's a video that explains what floating point really means. In addition to 16 and 24-bit recording, many digital audio workstations can now record at 32-bit floating point resolution. Floating point is a way of representing a number where the decimal point is not fixed at the division between integers and decimals, but can move or float. Scientists, engineers, and even computers use floating point, also known as scientific notation, because it allows numbers with vastly different orders of magnitude to be more easily used in calculations. The format for a floating point number includes the significant figures, the first few numbers with the decimal point after the first number, then the multiplication symbol x, followed by the base number, usually 10, but not always, raised to an exponent that indicates the number of places to the left or right the decimal moved. For example, the number 1000 written in floating point notation would be 1.0 times 10 to the third power, since the decimal moved 3 places to the left. A googol, which is an actual mathematical term for a number with 100 zeros, when written in floating point notation, simplifies from this to this. So when you're working in 32-bit, your digital number is 32 characters long. You have now 4,294,967,296 quantization levels, and your dynamic range is a whopping 192 dB. Where 32 bits really is helpful is when you're doing digital signal processing, because the DSP actually truncates some numbers. In doing the math, you round off numbers and numbers get lost. So you might start with a 24-bit file, but after you've done a bunch of processing, maybe now you have a 19-bit file or even something less. So with the 32 bits, you can actually maintain a fairly high degree of resolution. Many of the mastering platforms like Sonic Solutions, and now it's called SoundBlade, that mastering engineers used, you didn't have a high track count, but you did have a very high bit depth through all the plugins. So that meant that you were actually not degrading the signal at all. So having 32 bits, especially when you're mixing or mastering, is very helpful. So here's the good news. As you're increasing the file size from 256 quantization levels up to 4 billion, 294 million, etc. quantization levels, you would think that the 32-bit file would be astronomically bigger than the 8-bit file. But the file size is actually determined by what's called the data rate, which is simply the sample rate times the bit depth. So that means that a 32-bit file is only 4 times larger than an 8-bit file. It's a really wonderful feature when you can get like 1,000,000 times more definition and only increase the file size by 4. And here's a benchmark number that you should probably remember, and it's fairly easy because it's 10. And that's the size of a 44.116-bit stereo file, like a CD file. It's 10 megabytes per stereo minute. So you can do an easy calculation. For example, if a file is 3 minutes long, it's going to be about 30 megabytes. If it's 4.5 minutes long, it's going to be about 45 megabytes. And then if you want to figure out, okay, what's a 24-bit file, then you multiply that times 1.5. When Karl-Heinz Brandenburg in 1988 developed MP3 files, he was trying to get the sound of a CD file into a much smaller package. And he did that successfully, and we use MP3s now everywhere. Typically in this course, we work with what's known as the CD quality MP3s, and that's anywhere from 128 kilobits per second up to 192. I prefer the 192s, but if you want to use the 128s, in fact, radio stations typically use 128, you could do that. But you can see the data rate is, rather than 10 megabytes per stereo minute, now it's around 1 megabyte per stereo minute, depending on the higher end or lower end of that you go. And again, this is why I prefer that you submit MP3s as opposed to WAV, because I'm storing these files for you and it takes less disk space on my hard drives. And for deliverable files, the MP3s work just as well as the WAVs. Okay, so that's the end of this video, so continue on with the lesson.